This is Chapter 2, Linear Kinematics, Describing Objects in Linear Motion. The objectives for this chapter are to distinguish between linear, angular, and general motion, define distance traveled and displacement and distinguish between the two, define average speed and average velocity and distinguish between the two, define instantaneous speed and instantaneous velocity, define average acceleration, define instantaneous acceleration, name the units of measurement for distance traveled and displacement, speed and velocity, and acceleration, use equations of projectile motion to determine the vertical or horizontal position of a projectile given the initial velocities and time. There are different types of linear motion, or also referred to as translation. Rectilinear translation occurs when all points on a body or object move in a straight line so that the direction of motion does not change, the orientation of the object does not change, and all points on the object move the same distance. Curvilinear translation occurs when all points on a body or object move so that the orientation of the object does not change, and all points on the object move the same distance. The difference between curvilinear and rectilinear is that the paths followed by the points on an object in curvilinear translation are curved. So the direction of motion is always changing, even though the orientation of the object does not. To determine whether motion is linear, imagine 2 points on the object in question. Now imagine a straight line connecting these 2 points. As the object moves, does the line keep its same orientation? That is, does the line point in the same direction throughout the movement? Does the line stay the same length during the movement? If both these conditions are true throughout the movement, the motion is linear. If both points on the imaginary line move in parallel straight lines during the motion is rectilinear. If both points on the imaginary line move in parallel lines that are not straight, the motion is curvilinear. To determine whether or not a motion is angular, imagine any 2 points on the object in question. As the object moves, ask yourself, are the paths that each of these points follow circular? Do these circular paths have the same center of axis? If you imagine the line connecting the 2 imaginary points, does this line continuously change orientation as the object moves? Does the line continuously change the direction in which it points? If these conditions are true, the object is rotating. The first kinematic characteristic we might describe about an object is its position. Where is the object? Where is the object at the beginning of its motion, or at the end of its motion, or at some time during the movement? The position of an object is really defined as the location in space. To think about this more critically, in sport play, almost everything rests on a player's position. If he or she scores a goal, they must have been somewhat in proximity to the goal in order to do so. When we describe an object's position, we also might describe it as being relative to something else. For example, consider a runner competing in a 100-meter dash. How would you go about describing the runner's position during the race? You might say she's 40 meters from the start, or she's 60 meters from the finish. This position description is done so by describing the object's position relative to a fixed non-moving object, which would be the start or the finish line. While these references points appear to be fixed and non-moving, it is important to remember that the Earth is continually moving. Thus, it's difficult to define a position in terms of absolute non-moving reference frame. It is also important to note that the example about the 100-meter dash runner is only one-dimensional. So let's think of an example that takes place in 2 dimensions. Imagine a running back has broken out of the backfield and is running toward the goal line. He is on the opposite team's 20-yard line. At this point, we could probably all agree and say that his position is about 20 yards from the goal line. But to fully and accurately describe his position, we would need to consider it relative to the sides of the field as well. Using the left sideline as a reference, you could then describe his position as 20 yards from the goal line and 15 yards from the left sideline. In the case of the 2-dimensional football player on the previous slide, it might be helpful to set up a Cartesian coordinate system to help identify the location of the runner. Cartesian coordinates are named after a French philosopher and mathematician, Descartes. In order to set up a coordinate system, we would need to identify a reference point. This fixed point is called the origin, because all of our position measurements are going to originate from it. Considering the football player on the field, perhaps an easy location for the reference or origin would be at the intersection of the left sideline and the running back's goal line. Imagine the x-axis lying along the goal line with 0 at the origin and positive numbers to the right of the playing field. Imagine the y-axis lying along the left sideline with 0 at the origin and positive numbers increasing as you move toward the opposite goal. With this system, we could identify the running back's position with 2 numbers corresponding to his x and y coordinates in yards as follows. The x coordinate of 15 indicates that he is 15 yards from the left sideline on the field, and the y coordinate of 80 indicates that he is 80 yards from his goal line, or 20 yards from scoring. In the case of 3 dimensions, we would need 3 numbers to describe the position of an object in space. For example, how would you describe the position of a ball during a game of racquetball? We might set up a 3-dimensional Cartesian coordinate system with 1 axis in the vertical direction and 2 axes in the horizontal plane. If we put the point of reference in the lower left corner of the court, the x-axis would be the line along the intersection of the front wall and floor. The y-axis would be the line along the intersection of the front wall and the left side wall, and the z-axis would be the line along the intersection of the left side wall and the floor. If the ball were 3 meters to the right of the left wall, 2 meters above the floor, and 4 meters away from the 4 meters away from the front wall, its x, y, and z coordinates in meters would be 3, 2, and 4. To describe the position of something in space, we need to identify a fixed reference point to serve as an origin for our coordinate system. For our purposes, any point fixed relative to Earth will do. Then we set up a Cartesian coordinate system. The axes of this system may point in any direction that is convenient as long as they are at a right angle to each other if we are describing the position of something in 2 or 3 dimensions. The x-coordinate of an object is the distance the object is away from the plane formed by the y and z axis. The y-coordinate of an object is the distance the object is away from the plane formed by the x and z axes, and the z-coordinate of an object is the distance the object is away from the plane formed by the x and y axes. Some quantities that we are concerned with assessing in linear kinematics are velocity, acceleration, momentum, direction. These are referred to as vectors, meaning they have both magnitude and direction. Scalar quantities are those that only have magnitude. So if you need help really differentiating between scalars and vectors, I recommend watching the YouTube video, link provided at the bottom of this slide. Let's return to the football example. Suppose a football player has received the kickoff at his 5-yard line, 15 yards from the left sideline. His position on the field using the Cartesian coordinate system is 15 and 5 when he catches the ball. He runs the ball back following the path shown above. He is finally tackled on his 35-yard line, 5 yards from the left sideline. His position on the field at the end of play is 5 and 35. If we measure the length of the path of his run with the ball, it turns out to be 48 yards. We might describe this run as 48 yards to gain 30 yards, a run of 48 yards to gain 30 yards. However, another way of saying this is to say that the runner's displacement was positive 30 yards in the y direction and negative 10 yards in the x direction. In the example prior, the distance traveled by the runner was 48 yards. We've used 2 different terms to describe the runner's progress, displacement and distance traveled. Distance traveled is easy to define. It's simply a measure of the length of the path, followed by the object whose motion is being described, from its starting or initial position to its ending or final position. Distance traveled doesn't mean a whole lot in the football game, though, because the direction of travel isn't considered. Displacement does take into account the direction of travel. Displacement is the straight line distance in a specific direction from the initial or starting position to the final or ending position. If you recall from the first chapter, vectors can be resolved into components. In the football example, the resultant displacement of the running back does not indicate directly how many yards the back gained. But if we resolve this resultant displacement into components in the x direction, which would be across the field, and the y direction, or down the field toward the goal, we then have a measure of how effective the run was. In this case, the y displacement of the running back is the measure of importance. His initial y position was 5 yards, and his final y position was 35 yards. We can find his y and x displacement values by subtracting the initial position from the final position. Thus, the runner's y displacement, or displacement down the field, would be 35 yards minus 5 yards, which would be a positive 30 yards. The positive sign indicates that the displacement was in the positive y direction or toward the goal. On the other hand, the player's displacement across the field is 5 yards as the final position and 15 yards as the initial position. If we subtract 15 from 5, that gives us a negative 10 yards. And again, the negative sign indicates that the displacement was in the negative or x direction towards the left sideline. We could also determine the resultant displacement using trigonometric relationships. The displacement vectors arranged form a triangle, specifically a right triangle with a hypotenuse represented by the resultant displacement. The size of the hypotenuse can be determined using the Pythagorean theorem. If A and B represent the two sides that make up the right angle, and C represents the hypotenuse, then A squared plus B squared equals C squared. For our displacements then, we can substitute negative 10 yards for the change in x and positive 30 yards for the change in y, and then solve for r, which represents the resultant displacement. We then arrive at r is equal to 31.6 yards. To find the direction of this resultant displacement, we can use the relationship between the two sides of the displacement triangle. In this equation, theta, which is the angle that we are interested in, represents the angle between the resultant displacement vector and the y displacement vector. To find the value of theta, substitute negative 10 yards for the change in x and positive 30 yards for the change in y. Thus, theta is equal to 18.4 degrees. Are speed and velocity the same thing? Mechanically, speed and velocity are different. Speed is just the rate of motion, or specifically, it is the rate of distance traveled. It is described by a single number only. Velocity is the rate of motion in a specific direction, or the rate of displacement. Since displacement is a vector quantity, so is velocity. Average speed of an object is distance traveled divided by time, or divided by the time it took to travel that distance. Average speed is an important descriptor of performance in many sports activities. In some activities, average speed is the measure of success. Let's take a look at the 100-meter dash as an example. At the 12th International Athletics Amateur Federation World Championships in Athletics in Berlin in 2009, the men's 100-meter dash was won by Usain Bolt of Jamaica in a world record-setting time of 9.85 seconds. The second place finisher, which was Tyson Gay of the United States, finished in 9.71 seconds. We can determine their average speed by dividing the distance, or 100 meters, by the time in which the distance was ran. For Bolt, this would have been the 9.58 seconds. Thus, Bolt's average speed was 10.44 seconds, while Gay's was 10.3 seconds. If we wanted to break the race up into a bit more to determine how they differed throughout, we could look at the first and second 50 meters of the total 100 meters. From Table 2.2 in your book, we can see that Bolt was faster than Gay over every interval up to the 60 to 80 meters. During the 60 to 70 meter interval, both Bolt and Gay reached their maximum speed, and their average speeds during this interval were the same. After 70 meters, both runners slowed down, but Gay slowed down even more, especially over the last 20 meters of the race, from the 80 meter marker to 100 meters. So since we're talking about Usain Bolt, I thought it was only necessary to include a video of him participating in the 2009 IAF Championships. Pay special attention to his stride length compared to the other competitors in this race. It's pretty impressive. Moving to velocity. Average velocity is displacement of an object divided by the time it took for that displacement. Mathematically, this can be represented as the change is v is equal to d over the change in time. Average velocity is equal to d, or displacement, divided by the change in time. Sometimes we are interested in the component of velocity, or only interested in the component of velocity. So just as we were able to resolve forces and displacement vectors into components, we can also resolve velocity vectors into components. To resolve a resultant average velocity into components, we could simply determine the components of the resultant displacement. For the kickoff return, the football player's displacement from the instant he received the ball until he was tackled was negative 10 yards in the x direction across the field and positive 30 yards in the y direction down the field. His resultant displacement was 31.6 yards down and across the field, or negative 71.6 degrees across the field. To determine his resultant average velocity, we use the formula provided above. Average velocity is equal to distance divided by change in time, or equal to displacement divided by the change in time. Thus, his resultant average velocity was 5.3 yards per second. Similarly, the running back's average velocity across the field in the x direction would be the x component of his displacement divided by time, or the average velocity of x is equal to the change in x over the change in time, which gives us negative 1.7 yards per second. The running back average velocity down the field in the y direction, which is the most important of all these velocities, would be the y component of his displacement divided by time, or the average velocity for the y component is equal to the change in y divided by the change in time, which gives us 5.0 yards per second. Just as with displacements, the resultant average velocity is larger than any of its components. And just with the displacements, the square of the resultant average velocity should equal the sum of squares of its components. So a squared plus b squared equals c squared. If we input those values for our x and y components, that gives us 5.3 yards per second. It's important to note that if the motion of the object under analysis is in straight line and rectilinear with no change in direction, average speed and average velocity will be identical in magnitude. Acceleration is a term you are probably familiar with, but the mechanical definition of acceleration may differ from yours, so let's look a little bit closer. Mechanically, acceleration is the rate of change of velocity. Because velocity is a vector quantity, acceleration is also a vector quantity. An object accelerates if the magnitude or direction of its velocity changes. From this mechanical definition of average acceleration, it is apparent that acceleration can be positive or negative. If the final velocity is less or slower than the initial velocity, the change in velocity is a negative number, and the resultant average velocity is a negative number as well. This happens if the object slows down in the positive direction. A negative average acceleration will also result if the initial and final velocities are both negative, and if the final velocity is a larger number than its initial velocity. This occurs if an object is speeding up in the negative direction. Let's use the example of a car that can accelerate from 0 to 60 in 7 seconds. Therefore, the average acceleration for this car would be 8.6 miles per hour per second. The way to interpret this would be in 1 second, the car's velocity increases, or the car speeds up by 8.6 miles per hour. If the car is accelerating at 8.6 miles per hour per second and moving at 30 miles per hour, 1 second later, the car will be traveling at 8.6 miles per hour faster, or 38.6 miles per hour. 2 seconds later, the car will be traveling 2 times 8.6 miles per hour faster, 17.2 miles per hour, or 47.2 miles per hour. This figure represents the direction of motion, and the direction of motion and the direction of acceleration are the same when the object is speeding up, but opposite to each other when the object is slowing down. So I really recommend that you review this a couple of times to ensure that you understand how these variables may change. We're going to move and talk about projectile motion now. Not all objects that fly through the air are projectiles. A projectile is a body in free fall. All projectiles undergo curvilinear motion. So they reach an apex and then they begin to fall to the ground. Additionally, an object that is launched into flight is subject only to the forces of gravity and air resistance. In sport, there are 3 aspects of the trajectory that are most important. First, the angle. This refers to the angle at which the projectile is launched. If you can imagine a quarterback throwing a Hail Mary, you may imagine him releasing the football very high or at a larger angle in order to make sure its vertical and horizontal velocities are great enough to allow for the largest trajectory, hopefully near the end zone. On the contrary, if he is passing for a quick short route, you may imagine his angle of release being much smaller, as the ball does not need to have as much vertical velocity as seen in the Hail Mary toss. Speed refers to the speed at which it is released. The greater speed the object has, the farther its trajectory will be. And lastly, relative height. Relative height determines how long the object will be in flight. So let's take a little bit of a closer look. The relative projection height, or also known as RPH, is the difference in the height from which the body is initially projected and the height at which it lands or stops. Flight time will increase by increasing the vertical component of projection velocity or by increasing the RPH. A positive RPH means that the object landed at a height lower than that from which it was launched. A negative RPH means that the object landed at a height that is higher than that what it was launched. The latter thus means that the flight time will be decreased, right, corresponding to the negative value assigned to it. Above are the factors influencing projectile motion. As mentioned previously, the 3 most important aspects that determine trajectory, and the most important in sport, are initial speed, projection angle, and relative projection height. And then just to kind of wrap up, these are the formulas that we will be using for calculating horizontal and vertical distances and velocities, as well as release angles. While you don't have to have these memorized, it will be important to be familiar with those trigonometric functions in order to determine angle of release for some of these measures that we will be conducting. All right, that wraps up Chapter 2.